Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In today's video, we are going to talk about energy and temperature. What is energy? Probably the most correct answer is nobody really knows. But energy is something that matter has to possess to do work. And matter is everything that you see around us that occupies some space. Energy cannot be created nor destroyed, but it can readily change forms. Secondly, what does it mean do work? Well, work is very well defined in the concept of physics, but in this fundamental playlist where we don't go into heavy equations or anything like that, we could say that work means moving stuff around, things happening. So for things to happen, there has to be energy. And energy, as I said, comes in various forms. We have potential energy, and that is energy of being in gravitational field defined as mgh. M is mass of an object, g is gravitational acceleration, it's a constant that we already saw in one of my previous videos, 9.81 meters per second squared. And h is height above some reference level, which is very important quantity here. You see, my potential energy is my mass, 96 kilograms, times this constant, times height above what? Well, if I measure height above this floor, then my potential energy is 0. But because I am on the second floor, if I measure height with respect to Earth's surface, then this height is about 10-15 meters, so I have certain potential energy. So you can see potential energy is attached to the reference level to which we measure height. The second form of energy is kinetic energy, and it is defined as 1/2 mass, again, but times speed squared of objects. If object has no speed, it has no kinetic energy. Consequently, we say that kinetic energy is energy of motion. And you can already see right away that potential energy can be transferred into kinetic energy and vice versa. If here is Earth's surface, and as I said, I will use Z to indicate height. If we have an object here at a distance h above Earth's surface, this object has potential energy mgh. However, gravity will pull it down, this object will start going down, and it will start losing potential energy because age is decreasing, but it will gain kinetic energy. Eventually, it will hit the surface and it will lose potential, it will lose kinetic energy, but we said energy cannot be destroyed. So where will that energy go? It can go into heat, warming up a little bit surface. And that heat is defined again as mass times some constant C, which is called specific heat, and it's a property of the material, which means it is not the same if this object hits a rubber earth, water, regular earth, or something else, and times T, and T is temperature of an object in kelvins. Going back to kinetic energy, we can see that it is proportional to speed squared. So small changes of speed result in significant changes of kinetic energy, and this is one of the main concepts that we use in harnessing wind energy from wind and creating electrical energy using wind turbines. So heat is another form of energy, and lastly, we could say that radiant energy, we often just call it E, can be defined as H times F. And this is energy of radiation figured out by great Max Planck. H is a constant, Planck's constant, very, very small number. I think it is order of magnitude 10 to negative 34, I believe, joule seconds. And F is frequency of radiation. Radiation is electromagnetic waves. Let's discuss that. Here is a nice wave. Frequency can be defined as the number of times, let's say, this crest of a wave passes over a certain point. So this would be crest. This would also be crest. This would be trough. And over there would be another trough. Distance between two crests, for example, is called wavelength, and we often use Greek lambda to indicate that. But really, distance between any 2 points, now this is important part, that are in the same phase is wavelength. What do I mean by that? I don't have to go from crest to crest to define wavelength. In principle, I could go from this point and find the same point over here. This is also wavelength lambda. Now you might say, but this point seems to be the same as that point. So why not going here? It seems to be like this point, but it is not. Because you can see that here, curve is decreasing, curve is increasing over here towards the crest. So the right neighborhood of this point is not that point, but rather this point over here. Now, there is equation that says that c, speed of light, which is approximately 300,000 kilometers in second, is equal lambda times f, which means from this equation I can say that f is equal c divided by lambda. Plugging that here, I can see that radiant energy or radiation can also be expressed as h times c divided by lambda, where h and c are constants. C is speed of light, that is universal constant, defined, of course, through famous Einstein theory of special relativity. Everybody knows equation E equals mc squared, by the way. This is equation of humankind. But you can see that radiant energy is also inversely proportional to the wavelength of radiation. Why did I write all this? Well, to demonstrate to you, if you have a sorry about that. If you have a wave with much shorter wavelength, like this, that wave has much higher energy thanks to this Planck's equation, and we know that. We know that because, for example, ultraviolet waves are very high energy, but they have very short wavelengths, and they can cause burning of your skin and so on. On the other hand, radio waves and infrared waves, they have very long wavelengths, and because they have very long wavelengths, energy of these waves is very, very low. Out of all these forms of energy, radiant energy does not require medium to be transmitted. Carriers of this energy are called photons, the smallest particles that carry radiation, and they can travel through vacuum. And this is, of course, what is happening when solar energy is traveling through almost perfect vacuum from the sun to the earth. That is not the case, for example, for sound energy. This video would not be possible in the outer space, at least voice, because voice could not travel between my mouth and this microphone here or camera over there, whatever is recording this audio. Lastly, I would like to connect this concept of energy a little bit with temperature. What is temperature? We often indicate temperature with capital T, and temperature is either given in kelvins or in degrees Celsius. In United States of America they use Fahrenheit, but I will not use Fahrenheit in this playlist. Kelvin is the absolute scale of temperature. Temperature of 0 Kelvin is also known as absolute zero. We cannot achieve temperature lower than 0 kelvins. Switching between kelvins and Celsius is very, very simple, because temperature in degrees Celsius is temperature in kelvins minus 273.15. So, for example, 0 kelvins is equal, as you can see, negative 273.15 degrees Celsius. And so on, you can convert now whatever you want. What is temperature in relation to the energy that I defined before? Well, temperature turns out to be related to kinetic energy. And you remember kinetic energy was 1 over 2 mv squared. Average kinetic energy of atoms and molecules of air around me are proportional to temperature. Average kinetic energy of motion is a measure of temperature. High level of this kinetic energy means high temperature. Low level of kinetic energy of atoms and molecules means low temperature. Given that mass is constant of nitrogen, oxygen, these are not radioactive elements around us. Given that mass is constant, we can say that kinetic energy is really just measure of the average velocity squared of molecules and atoms around us. This also tells you why cold air is more dense than warm air. Let us examine that further. Let us say that, let's go to the next page to do this properly. So, as I said, kinetic energy is proportional to V squared, and that is proportional to temperature. That is just what I discussed now. Let us say low temperature here. Low temperature, and let us examine here case of high temperature. In the case of low temperature, we have atoms and molecules that are moving around randomly in any given direction, but their speed is not high, indicated with these short arrows. So this is perhaps space that they would create for themselves because they are jiggling just a little bit. So this would be low temperature, and you can see it is related to high density. You will remember I used Greek rho for density in my previous videos. Now high temperature, let's see, we have 1, 2, 3, 4, 5, 6 atoms. Because these atoms on average have much higher kinetic energy, that means they are moving much faster, they tend to occupy bigger space. This is in 3 dimensions. So you can see that high temperature means low density. Because in both cases I have 1, 2, 3, 4, 5, 6 atoms or molecules. So you know from my previous video that density is mass over volume. Mass is the same, but volume here is larger than volume here, and that means this is low density, this is high density. But volume here being large is a consequence of high temperature of this gas compared to low temperature of this gas. And in turn, temperature is related to the square of the speed of these atoms, and that in turn is the concept of kinetic energy. In this video, therefore, we covered various forms of energy that are important in atmospheric sciences and physics in general, and we saw a relationship between kinetic energy, speed of atoms and molecules in the gas, their temperature, and then we connected it with one of the previous lectures where we talked about air density. Until next video, goodbye.